flow assurance is to ensure, what is the flow assurance? Flow assurance is that it's something new, maybe 30 years old, and it was the terminology first used by Petrobras, the Brazilian oil company, and basically said that ensuring the fluid transfer from reservoir to end user in controlled manner and economical. That's basically flow assurance. And it will include solid formation, like hydrate, wax, asphaltene, scale, include the flow regime, include corrosion. So it's a wide range of expertise. And it is now being as an independent category in some universities. But you can see that in a job description, we have flow assurance engineer. So it is very important. So what we are doing here and ensuring production system is correctly sized and specific to achieve a certain situation. First of all, we want to have be able to deliver, and integrity does not fail because of corrosion, erosion. We can control the flow, and the production is not interrupted because of all the solid that can fall or liquid can fall. It is a science between subsurface and surface. Yeah? And it balances input from reservoir with the demand from production. And obviously it will depend on production, fluid characteristics, and flow conduit. So question for flow assurance engineer is that, do we have gas or oil? Do we expect water production? What lab tests we need to do? Are the fluid untreated or treated? Yeah. And do we need processing? Because obviously you can do processing at the point of production, and then don't be worried about or reduce your worries about flow assurance. But most of the time is not cost effective, especially offshore. And there is the distance between receiving facilities and the where we are producing, that play a major role. The longer, the more flow assurance problem you can expect. And then ambient condition. What are different constraints we have? Pressure, temperature, and receiving facilities. And then also think about future, because offshore installation are expensive. So you normally start with the reservoir which has maximum capacity. But once that reservoir is depleted or partially depleted, you need to think about connecting to other reservoir, okay? And normally, when we have a major reservoir, there are some smaller reservoir nearby, okay? Because you can have different anticline, and the oil and gas can go to different anticline. So the corrosion include hydrate, flow assurance. It will include hydrate, corrosion, wax, asphalting, scale, sand production, other issues like emulsion, foaming. So you see that it is a large area, and it is fantastic. And you know, that's why when I started my work, it was not flow assurance. We didn't call it flow assurance. But now I'm very happy to see that as a separate category of job, and also petroleum engineering is defined as a different category. And heat transfer, hydraulic, and then a steady state production, shutdown, and a startup. You know, three conditions. We can have a startup that has a different issues. A steady state has a different issue. Shutdown would have a different issue. So you need to address all these three conditions, okay? And the phase envelope is very important. The fluid phase envelope is very important, okay? So we need to basically plot this phase envelope. Are you familiar with phase envelope?
Yes.
We are in the process, yes.
Yeah. And normally, basically, phase envelope depends if you have the composition. If you have the composition, you can plot phase envelope. The problem is that for components that are heavier than C7 plus, we don't know their critical temperature and pressure and asymptotic factor, because we need these three parameters, critical pressure, critical temperature, and asymptotic factor, to model the system. And therefore, normally our prediction is wrong. And that's why we need lab tests to measure bubble point, dew point, or different property, and then tune the equation of state to match this condition. So here we are matching the bubble point. This is bubble point. This is critical point. This is dew point, and this is 90% liquid, 80%, and from here 10% and 0%. Okay, so that is the phase envelope. It is very important. The first thing you need to do is plot the phase envelope, and then once you know the phase envelope, now you are producing from this reservoir. Reservoir condition is here, and initially in above saturation pressure, and then now here goes inside. When it condition goes inside two-phase region, the fluid become two phases. Now you have gas, liquid, and maybe three phases. You can have water, or four phases. You can have wax, asphaltene, so you can have different problems. So now you have a certain path you have chosen, for example, but and you need to plot wax condition. This is a wax condition, and at bubble point, that's the reason we need to plot this phase envelope correctly, because at bubble point, at below bubble point, if you increase pressure, this is pressure. If you increase pressure, the amount of light component will be increased in the hydrocarbon phase, in liquid hydrocarbon phase, and that will reduce the concentration of heavy component. Therefore, wax formation will be more difficult, and you need to cool down more. So the bubble point, at bubble point, there is no gas. So when you increase pressure above bubble point, now the liquid oil conversion to wax, the volume is reduced. Also, increasing pressure will reduce the volume. Yeah, if you have a fluid, you apply pressure, the volume is reduced. So you see that wax formation and pressure increase, they are in the same direction. So that's why you see that the phase envelope for wax shifts to the right, while here below bubble point, it shifts to the left. So knowing the bubble point is very important to plot this correctly. And that's why we need to do first tuning of equation of state to match the bubble point. Okay. Now hydrate, similar issue. Okay. Now you see that in our production approach, we don't have hydrate problem, but you can have wax problem. Okay. We plot this figure to find out what sort of problem we have. Now, the weak point of this approach is that the receiving pressure would be very low here. So we can assume a different approach. Yeah. So you look at different approach and see that, for example, this approach with a slightly high pressure, but it's still out of the hydrate. And then this approach will have hydrate problem and wax problem. Yeah. So you need to have all these figures to make decision which path to take. And now this is asphaltene phase envelope. This is upper asphaltene onset. This is lower asphaltene onset. And we need also to plot this one. And then a scale formation. Yeah. These are different scale formation. So you need to have this full figure to predict, and this is viscosity increase. Yeah? Below bubble point, as you reduce pressure, the viscosity increases. So you see that you need to have the prediction for all of this to be able to predict what sort of problem you have, and decide which way to move, and how to solve problem. Here, this is hydrate phase boundary. This is hydrate phase. Phase envelope of a gas you see that this is critical point. This is condom term. This is condom bar, and this is condom term. And what type of fluid do we have in the reservoir? Clearly, you see that the cry-condom term is around 40, minus 40. Okay? So above minus 40, we have single-phase gas. So this is gas. Is it dry gas or wet gas? This is a dry gas because separator condition is around 15 degrees. So it doesn't go two-phase. So we need to have this phase envelope, as I mentioned before. And this is an oil, okay? An oil condition, you see that this is a critical point. Cry-condom bar, cry-condom term, yeah? And the reservoir condition, normally reservoir condition is around 100 degrees. So you see that this is an oil because the temperature of the reservoir is below critical point. And then when we are producing, the pressure will drop. In the reservoir, pressure drop of like here, and then we are producing, move this way. So we can have all sorts of problems. So that's the reason we need to plot this. This figure is very important. Yeah. Here you see first the phase envelope. The first thing you need to do to tune and match phase envelope. That's why lab data is important. And then you can add hydrate phase boundary, you can add wax phase boundary, you can have asphaltene phase envelope, you can have carbonate phase envelope, you can have SrCO2 problem. This is barium sulfate problem. You know, you need to, then you decide which way you want to go. And obviously you want to avoid as much as many as possible. Yeah? You see that here, if you move this way, you have asphaltene problem. But if you move this way, you don't have asphaltene problem. Yeah? And then here at the very end, you might have some asphaltene problem, but you have wax problem. Yeah? And here you have hydrate problem. And then, you know, the operating condition goes barium problem here. And, you know, you don't have the calcium carbonate. You know, you can see all sorts of problems you can have. Is clear for everybody so far?
Yes, sir.
I think yes.
Excellent. So what we need, once we know the composition, then we can, normally we can predict density, viscosity, or at least do some experimental work and then predict these properties, surface tension, thermal conductivity, specific heat. They are all important, but obviously some more important than others, you know. Have you read the animal farm? You know, so here but depending on what sort of problem we have, we need to consider the mitigation, prevention, or using inhibitor and things like that. Okay, so we need to have, first, the point is that to have characterization. Characterization is grouping the pseudo component in different groups and then defining critical property and authentic factor to match the experimental data. So here we discuss hydrate, wax, asphaltene, scale, foam, and emulsion. Hydrate. Hydrate are what they are. They are components similar to ice. They look like ice, but the difference is that they have a lot of gas inside them. and they can form at temperature much higher than 0. We can have hydrate, depending on gas composition, at 20 degrees. So, so that's the big. There are two big differences between hydrate and ice. Is that hydrate can form at temperature above 0, and it has a lot of gas inside them. Yeah, a lot of gas inside them. Here we discuss the aspect and conventional mitigation option, potentially new solution. So each molecule, each compound can be in 4 stages. We know 3 stages, but there is I explain. First of all, gas state. Gas state when the molecules are separated from each other. When they are separated, it doesn't matter which molecule is there, because they are separated. They don't have a lot of interaction. So, for example, water can go inside the gas molecules, between the gas molecules. Yeah. And gas state, the molecule will fill the container, completely fill the space available. If you increase, again, pressure, the same thing. They will completely fill the, imagine that you have a bottle of water, remove the water, now you only have air there, and everywhere is the same, okay? Completely fill this space. Liquid state is when the kinetic energy of the molecules reduce, they attract each other, and they are touching each other. They are touching each other, but the point of attachment is not fixed. It can rotate. So you see that liquid is not compressible. But if imagine that you have that bottle of water I mentioned to you, and you have water inside that, but not completely filled, and then you can rotate the bottle, and if it takes the shape of the container, okay? So you can form, different shape. So, but it has a level, yeah? It has a level, but if you, put it horizontal, would be different shape. If you put the vertical, would be different shape. So it takes the shape of the container. Solid state, when the movement of the molecule is reduced further, and the position of attachment is fixed. The position of attachment is fixed. If you have water in the form of ice, then its shape is fixed. If you turn the bottle, it doesn't make much difference. Okay? So it has its own shape. Another state is plasma. Plasma, whatever we see of the world is majority of plasma, because we see the stars and they are a plasma state. There, the movement of the molecule is so high that when they collide with each other, they remove the outer layer electron. So they become polar. And that's why the plasma TV will work. Yeah? And one point that if we have a change of a state from, for example, vapor to liquid, from liquid to solid, there is an element of heat transfer. Normally, gas conversion of the gas to liquid creates heat, exothermic. That's why burning your finger with hot water and steam would be different. Which one is more difficult, more damaging? From steam, if you burn your finger with steam, the temperature, one is the temperature of the steam, and then the steam become liquid on your finger, and that exerts extra because exothermic, so create more damage to your skin. Yeah. And so any change in state is what is called latent heat. Latent heat will happen. Okay. Now, molecules of water have very strange behavior. Now, water, it has 8 electrons in the outer layer. So here we have a cloud of electrons, 2 electrons here. Another will be here, 2. 1 electron shared with hydrogen, another electron shared with hydrogen. Now you have 8 electrons in outer layer. And then because oxygen has more electronegativity, the shared molecule, the shared electron, is rotating between more around the oxygen and less around the hydrogen. So therefore, the hydrogen part becomes partially positive, and here become partially negative, and this creates what is called hydrogen bonding. And hydrogen bonding is a very strong bond. So in the normal condition, this sort of shape will be made by water molecule. But when you have gas, in addition to hydrogen bonding, there is a wonderful forces between water molecule and the gas molecule. So the attraction is more. Earlier we said that increasing, when reduce the mobility of the movement of molecules, that will result in molecules changing phase. So if you have hydrogen bonding only, it will, it has a certain amount of force and it will freeze, although we should say melt, because freezing happens below 0, but we say that water will freeze at 0. So if I increase the hydrogen bonding, imagine that I have a device that can increase the hydrogen bonding. Will it freeze at higher temperature or lower temperature? at higher temperature.
Higher, yes.
Yeah. So if you increase the hydrogen bonding, water freezes at 5 degrees. If you reduce hydrogen bonding, will go -5. Yeah. Because if you limit the movement of water molecule, it will freeze. Yeah. The whole point of moving from gas to liquid and then solid is reducing the movement of the molecules. So if you have a gas molecule in between, in addition to hydrogen bonding, we have van der Waals forces. Therefore, the solid shape of the ice will form at higher temperature. But the difference is that there is a gas molecule inside. Okay? That is called hydrate. Now, you see that for hydrate formation, you need water or ice. You need water or ice. And then you have suitable size gas and liquid molecule. Why? Because in an open system, the molecule can move. But here we have water molecules. And the water molecules, the angle between this sharing the hydrogen molecule electron with hydrogen, this angle is 100, this angle here is 104.5 degrees. Okay, so the angle here between here or 0.5 degrees. Okay, so it's like a Lego game. Lego games, so you can make certain shape. You can make certain shape. You cannot make any shape. You have certain shape. And the molecule do not move towards each other. Yeah. What happened? The hydrogen bonding force, okay, that's there, but the van der Waals force depends how big the molecule is. Yeah. If the molecule is big, then it's closer. If it is too big, they repel each other. If it is too small, the force is less. So the hydrate formation depends which type of gas molecule we have. For example, C3 is a good molecule. IC4 is a good molecule. Yeah, they are spherical. They are the right size. But N2 is very small. C1 is very small. C2 is better. CO2 is polar, so it is good. H2S is polar as good. They can promote hydrate formation. So the position, this hydrate phase envelope, depends on the composition of the gas. Okay? So the higher, normally the best molecule is cyclopentane, for example, because it's spherical and is a good size. But cyclohexane is slightly bigger, so it is more difficult for cyclohexane to form hydrate. And then depend on the water condition. water condition. Because if you have something dissolved in the water, there would be less water molecule for forming hydrate. So the hydrate phase boundary shifts to the left. So if you have a spherical molecule, hydrate phase boundary shifts to the right. So that is the important figure that you need to plot in the very beginning. Can we have a 5 minutes break before? So the important point in hydrate problem is plotting hydrate phase boundary. And we can do it experimentally or modeling, or both of them. We have, the necessary equipment and facilities to do that in our university and company. And now, where we can form hydrate, so hydrate formation, you can see hydrate formation here. This is temperature probe. This is water gas interface. The connection is gone. I assume you can hear me. Can you see the video? You should be able to see video now.
We can see, but we can't hear.
No, there is no voice there.
Okay, okay.
Yeah. You see that hydrate is forming at the interface, and here was wetted by water. But you see that the interface work as a barrier. You see that the liquid remain as liquid water, and there are some strict going inside, and that's why in shutting condition, you might have this sort of condition that the hydrate formed at the interface and work like a barrier for further hydrate formation. And then when you start, that barrier is removed and then can block the whole pipe. And hydrate is source of energy. The source of energy. So we can look at Can you see the video?
No, we can hear something, but we can't see.
Okay, second. The magic of hydrate.
Now, yes, we can see it.
I play a role in this video. What is my? This is one of my staff and students. See that? Water is dropping, and my role was, that is my hand. You see that? I have the lighter. That was a program we created for this geology TV channel, National Geographic TV channel, and my friend has a very good Scottish accent, and he did the presentation. If you are interested, I can show you more.
The 1980s. Geologists start scanning the continental shelves and slopes with side-scan sonar. They find they are riddled with strange features. Giant craters thought to form when gas suddenly escapes from the sea floor. Some people even speculate that escaping gas could sink ships and may explain the mysteries of the Bermuda Triangle. Gas escapes are certainly dangerous. This oil rig off the coast of Norway is sinking into a bubbling sea of gas. The gas pours out after the rig's drill hit a pocket of methane gas. Hazards like this send geologists racing to explore the seafloor. On the edge of the continental shelf in the Gulf of Mexico, a team of scientists prepare to dive. Their mission: to investigate a strange substance that could be causing gas emissions from the seabed. Protected inside the 5-inch thick acrylic sphere of the Johnson Sea Link submarine, they plunge to the continental slope. 1,800 feet down, they find what they're looking for. A mound of a yellowish-white icy substance called methane hydrate. It forms under intense pressure at depths greater than 1,000 feet, and it contains gas. At Heriot-Watt University in Scotland, geologist Ross Anderson studies methane hydrate. Although methane hydrate is mainly made of water,
this is our lab.
It contains a lot of methane, as Ross Anderson is about to demonstrate. This gas burns, but don't try this at home.
It's actually slightly warm, but the cold water, as it melts, is cooling my hand. So right underneath it, it feels very cold, in fact. But I can feel the warmth of the flames where my hand is dry.
Methane hydrate holds so much gas that every cubic inch of ice releases 160 cubic inches of methane. Deep down on the continental slope, the gas is normally safely locked up in the methane hydrate. But if the temperature or pressure change, the hydrate can melt and the gas escapes. Its sudden release can cause blowout craters. But some people think it could do far worse. Research suggests it could sink a ship. At Monash University in Australia, physicists carry out an experiment in a test tank. They launch a bubble at a scale model boat. If the boat's in the wrong place at the wrong time, it sinks again and again. No one has ever reported a ship sunk by a gas bubble, but some people think methane hydrate might explain the disappearance of ships in the Bermuda Triangle. And methane hydrate is grabbing attention for another reason. Around the world, it's estimated there are up to 400 million trillion cubic feet of methane hydrate buried in the continental shelves and elsewhere in the ocean. By some estimates, that's more than twice as much energy as all the world's oil, gas, and coal reserves. It's difficult to extract, but this strange substance could be the fuel source for the future.
Okay. Any question? Interesting, huh?
Sir, how many papers do you have on gas hydrates?
Oh, I don't know. I have a lot. I have around 460 paper, probably half of it on hydrate. Because that was the area that let me tell you a story. Okay, so now the point that we mentioned about hydrate in sediment, this is hydrate phase boundary, pressure, temperature, and in water, in ocean, this is depth of water is pressure, isn't it? For every 10 meter water, the pressure increased by 1 bar. So 30,000 meter is 300 bar. That's why this was the way we calculated pressure in the reservoir. And imagine this is temperature. If you rotate this figure, you get this. So hydrate phase boundary would be this area. And now, so this is the area that hydrate can form, temperature and pressure condition. But instead of pressure is depth, because depth does the same effect. And this is the temperature. Surface temperature is high, and then subsea temperature is low, here 4 degrees. And 4 degrees is normally sea bottom temperature, because 4 degree water is the heaviest water. And this is geothermal temperature gradient. And temperature increases by 30 degrees Celsius per kilometer. So you see that hydrate can form here. This is hydrate condition, inside hydrate, and then up to here. Yeah, up to here can form hydrates. From here, depth, what depth? Around 500 meter. And then to, depend on, can be more, but this is the area that hydrate can form. For hydrate formation, we need 3 conditions. We need the right temperature, the right pressure, and that's the right temperature and pressure. We need pressure, and the water will create the pressure. and temperature profile, and then we need presence of water. We have plenty of water, but what else we need is presence of gas molecule. Where the gas molecule is coming from. So gas molecule, we can have conventional reservoir at higher depths, and they are not 100% C. They are not 100% C, and therefore some gas will come out. Okay, some gas will come out, and also here we have, organic material from decomposition of marine life. You have plankton and things like that. Here, the water depth is not that much high, so bacteria can live there. Yeah. So bacteria will eat this organic material and create gas. And the gas is methane gas, like cows, okay? They eat grass and they create methane gas. That's why you're playing a major role in global warming. So, so the gas coming out of the conventional reservoir is called thermogenic gas. Thermogenic, because of increasing temperature, they produce gas, and the gas coming from bacteria activity, we call it biogenic gas. And the gas is produced here and will be trapped in form of hydrate. But gas here, although hydrate can form, but because hydrate is lighter than water, move upward and come out of the hydrate zone and dissociate, okay? So in the sediment, we can have hydrate. This is permafrost. Surface temperature is sub-zero, and then this is the hydrate stability zone. Here is 0, and then, so temperature versus depth, the slope will change. But you see that again, we have a region that hydrate can form. And this is another video, it's not connected, but we can find a lot of places around the world that can form hydrate. You see that Mediterranean Sea is not that deep, but Black Sea is deep enough to form hydrate. Needs to be more than 500 meters. And you see that these are the places around India. They found some new in China and Japan, places, and many other places. And the amount of carbon in gas hydrate is twice all recoverable and non-recoverable oil and gas and coal. So 10,000 gigaton, yeah, and carbon, and then here is 5,000. And some people say that it can play a major role in gas supply. But I'm not sure at the moment, because although it is a stepping stone, but we are moving away from hydrocarbon reservoir. So initial would be moving away from coal, and then oil, and then gas, but they won't be completely removed, because before coal we were using goods, and still there are some places that we use. So there would be a mixture of various energy sources. And I show this video, and it can hydrate formation in the pipeline can. This is a peak receiver and can block the line altogether. So we need to have this information, light component, non-hydrocarbon, heavy component, and we need to have information whether we have salt, alcohol, because they will affect hydrocarbon. This compound will affect the aqueous phase. Okay, and this aqueous phase dissolve this component and shift the hydrate phase boundary to the left. And there are different techniques to test and find the hydrate phase boundary, and correlation, thermodynamic model, and the option for avoiding hydrate problem these are the main options. Water removal, dehydration, increasing system temperature by insulation and heating, reducing the system pressure, injection of thermodynamic inhibitor, and using this new category of low dosage hydrate inhibitor, kinetic hydrate inhibitor, antiagglomerant, and various combination of the two. And there is a new, I won't say new, around 20 years old concept, cold flow, that if you are interested, we can discuss these after the lunch break. I think I stop here. We go for, okay. So in general, these are the main option for avoiding hydrate problem. These are the main option. And we discussed this option, not all of them, but the one that, you know, the name showed what we mean, you know, because if you remove water, then obviously hydrate phase boundary shift to the left. And the more water you remove, it should move to the left even further. So that's one. The other one is maintaining the temperature. That is by insulation or heating. We can reduce the pressure. That will move from outside hydrate phase envelope. But pressure is energy. We don't want to lose energy. So this is normally, this option is kept if we want to have a blockage and we want to remove the blockage. The other one is that injection of thermodynamic inhibitor. Thermodynamic inhibitor are the inhibitor that basically they shift the hydrate phase boundary to the left because they dissolve in water. Just the heating is too high. I'm just so thermodynamic inhibitor, they dissolve in water, because some water molecules are busy dissolving this inhibitor, so there would be less water for forming hydrate. This is by far the most popular technique. Another technique is using low dosage hydrate inhibitor. Now, thermodynamic inhibitor are main weak point of thermodynamic inhibitor that you need a lot of it. And therefore, storage costs become an issue, especially for offshore, because offshore you have two major limitations. One is footprint, and another one is the weight. Offshore rigs, they have a limitation on weight and area available. So when you need inhibitor, large amount of inhibitor, you need to have a pipeline, which is expensive, or a storage on the platform, that is also expensive. So the industry has moved to what is called low dosage hydrate inhibitor. These are inhibitors that the concentration is between 0.5 weight percent or volume percent to 3%, compared to methanol, glycol that you need between 30 to 60%. So it is a lot more cost effective from that aspect. And they were discovered initially that some fish in Arctic region, although temperature of water is below zero, they can live. And they found that there is a protein in their blood that prevents freezing of their blood. And then they extracted that and then find that these are, we can make them chemically. And then they started to use that. And anti-agromanans, they don't prevent hydrate formation. In fact, they might encourage hydrate formation, but they prevent hydrate crystal sticking to each other and forming a blockage. And various combination of these, you can use, thermodynamic inhibitor with kinetic hydrate inhibitor or anti-agromanan. You can use inhibitor with insulation. You can do various options. The last option is cold flow or hydroflow, is that we don't prevent hydrate formation. We don't use any insulation. We don't use any heating. We don't use anything, and just manage in a controlled manner to form hydrate and transport hydrate as a form of a slurry. So that is, to some extent, is being used at the moment. This is a hydrate phase boundary of a gas mixture, and this is our operating point. And you can see that at the moment, the operating point is inside hydrate phase boundary. And obviously, if you add inhibitor, for example, methanol, 10% methanol, shift the hydrate phase boundary here, 20% shift here, 30% shift here, but 30% is, to some extent, is more than what we require. And then you can see that 26% is the exact number you want. Obviously, we also sometimes include a safety margin. Avoiding hydrate using kinetic hydrate inhibitor, they basically, the common understanding is that they prevent hydrate formation for a period of time. The way we test it, we put it in a cell and we reduce the cell temperature. You see that? And the temperature here is 4 degrees. So this is seabed temperature. And then you see that the pressure drop because temperature drop will contract the gas and the pressure drop. But you see that the pressure remain constant for, this is 1400. Let's start 200, 200, 1200 minutes. 1200 minutes is equivalent to 20 hours. So this chemical can prevent hydrate formation for 20 hours. If the residence time of oil and gas and hydrocarbon in the pipeline is less than 20 hours, then that's fine. This inhibitor will prevent hydrate formation for 12 hours. This is the old fashion of testing, but we now understand that it is not as simple as that. And we can basically understand better. Anti-agglomerant, what they do not prevent hydrate formation. This is without anti-agglomerant. You see that they are sticking to each other. This is with anti-agglomerant. You see that a small crystal. Here, a small crystal. So they all also are being used, but they are mainly used in United States. This is some tests when we have anti-agglomerant. You see that if you don't have anti-agglomerant, you see that the torque increases and basically the cell is blocked and this rotation is stopped. But if you use anti-agglomerant, you see that there is no blockage. Now, we have developed some new devices for monitoring hydrate problem, monitoring hydrate safety margin. But in general, as we discussed, for plotting or drawing the hydrate stability zone, you need two information. You need hydrocarbon phase and you need aqueous phase. Hydrocarbon phase doesn't change in short periods of time. If you have a reservoir, the composition of that reservoir does not change very quickly. But the water composition can change very quickly. The amount of salt can be increased, and the inhibitor we inject a certain amount of inhibitor. If the water cut changes, the concentration of inhibitor drop, and the system can go into the hydrate region, basically, and cause blockage. So what we do here, so we know the hydrocarbon phase, we need to find aqueous phase. And these are the reasons that system, human error, and some equipment may stop working, water cut, we always don't know what is the water cut, changes the pressure and temperature, or inhibitor that we are buying or are producing is not the purity that is written in the based on design. So basically what we need a quick system for measuring water composition. You can send it to the lab, but it takes time to get it from the lab. So this is the device that we have developed. We measure electrical conductivity and we measure the speed of sound. And with these two measurements, we can find two unknowns. And the two unknowns is salt, thermodynamic inhibitor, or kinetic inhibitor. So it is only 5 seconds. So it is very quick and basically real time. And then from that, we know hydrocarbon composition, we know now water composition, then we can plot the hydrate phase boundary. Then we can use some monitoring devices or computer program, Olga and things like that, to find the pipeline condition, pipeline pressure and temperature. Ideally, you want to keep the pipeline condition outside hydrate phase boundary. So one way is that to increase the amount of inhibitor. Here you see that the pipeline condition goes inside hydrate phase boundary, and therefore hydrate can form. Then we need to increase the amount of inhibitor. And if you want safety margin, then ideally you want to have the amount of inhibitor that can create this green line. If your hydrate phase boundary is this blue line, then you are injecting too much inhibitor, overdosing the system. So this device has been used and resulting in saving of millions, hundreds of million pound inhibitor and production. In one case, it increased the production from one reservoir by 5 years. And this was, this resulted in university winning the Queen's Anniversary Award in 2015. And I was there in Buckingham Palace. But if you are interested, I can send you the video. The university got the award on behalf of all the researchers. But it was a brilliant moment. And then here is some of the publication that has been published. The other device that we have developed is HydroSense, early signs of hydrate formation. Different components, they have different affinity to form hydrate. You see that here isobutane is strongest in the forming hydrate, then it's propane, then it's ethane, then it's methane. So when hydrates form, then what will happen, the concentration of these gases from gas phase will be reduced because some of them have formed hydrate, and hydrate density is similar to water density. So hydrate will follow with water. They don't travel in the gas phase, but the gas phase has changed. And this is the point I mentioned earlier on. Imagine that you have two molecules, one molecule is here, one molecule is here, yeah, far end here. And this is, can be gas and water. So maybe this is the water and this is the gas. And when they are far away, interaction is zero. There is no interaction between them. When they get a bit closer, it will result in shift of charges on the molecules. So imagine that you have two molecules. Imagine that you have two molecules, and then when they get close to each other, their shape will change, and they have a positive and this have negative. yeah, and they attract each other. And then, so they attract each other, and this is the size. In case of hydrate, the molecule cannot move, just the size of molecule determine where we are. So for cyclopentane, maybe we are here. So maximum attraction. For cyclohexane, we are here, yeah? If the molecule are too big, they repel each other, yeah? If they are far away from each other, they don't know each other. When they get a bit closer, they compromise, yeah? They basically negative and positive. When they get too close, they repel each other. A little bit like human being, you know? When we are, there is an optimum distance, keep peace and quiet. When they get too close, then they repel each other. As a joke, okay? This is a usage of the this device in a gas field in France. And here, this is the gas production, come to a vertical separator. The gas, there's a mesh here, and then the gas goes to the top, liquid goes here, liquid and water are together, liquid condensate and water together. And normally they have problem blockage here. They initially was using methanol, but once the concentration of water increased, then methanol was not cost effective. They use antiagromanant, so prevent hydrate blockage. But at the same time, in Total Gas, Total company was a sponsor. They use this device and put it here, and then monitor the composition of the gas. And then this is the result. You know, C1 to C3, C1 to IC4. So if hydrate form, concentration of C3 will be reduced, yeah, because in the gas phase, because the hydrate absorb the hydrate C3, and then concentration of IC4 is reduced. And because they have to add up to 100, concentration of methane will increase. So this move upward, okay? And then, so this, when hydrates form, this ratio will increase. And then when hydrate melted, this ratio reduce and then increase. Yeah, and they were a bit confused why it is increasing and dropping. Then we realized that that is something to do with day and night. And during nighttime, it was forming. During daytime, temperature increased, it was melting. So basically, they were injecting not antiagromanant for the whole year, but in fact, they need only for 10 days during the year.